these useful skills to fix timing. Actually, this useful skill is there, but we need to use it to fix timing. Okay, so let's so the bottom line useful skill is something that we add to fix that up on whole time. Okay, to fix that up a whole time violations. Okay, so let's take a look at this timing path. So we have two different rest to rest path, FF1 to FF2, and then FF2 to FF3. Okay, so this is the clock insertion delay on clock flop one, clock size two, clock size three, clock 2.5 seconds. So basically, the clocks arrive all three flops at the same time. So you really have zero clock skew. Okay, clock to queue timing 1 nanosecond. Setup is 1 nanosecond. Okay, and then clock period is 10. So to go from here to here is we allow 10 nanoseconds. Okay, so let's first take a look at flip flop one to flip flop two timing from rest to rest here. Okay, you recall the setup slack is equal to required time minus arrival time. Okay, so arrival time of this data here at a flip flop two is so clock delay plus clock delay is 2 nanoseconds. T data, which is data propagation here, 9 nanoseconds, plus clock to queue, 1 nanosecond. So 291. So the data arrival here at the capture flop for this first path is 12 nanosecond. That's the arrival time. Okay, you follow me? It's very important you understand this and you see how useful skill is going to help us. Okay, so the data arrival time at this flop is 12 nanosecond. Okay, now what is required time? The required time is clock periods plus clock delay minus setup time. So period is 10. Okay, the clock delay here is here is 2 nanosecond is 10 is 12 minus setup time. So the required time is 11 nanosecond. Okay, so from here to here, required time is 11 nanosecond. Okay, the setup slack is required minus arrival time. So we have 12. We have required time of 11 minus 12. So we have a negative slack, which is a violation. So the data arrive later, 1 nanosecond later in the required time. So we have a violation from flip-flop 1 to flip-flop 2 of 1 nanosecond. Okay. Now let's take a look at flip-flop 2 to 3 timing path. In the same manner, you can see the clock delay is 2 nanosecond, propagation delay for data is 5, plus clock to queue is 1. So the data arrived from here to here is 8 nanosecond. Okay, we know that. Okay, we know the clock period is 10. Okay, so what the required time here is clock period plus clock delay is 2 is 12 minus setup time. So that's 11. So setup equal required minus arrival time, 11 minus 8. So the data arrived at 8. So we have 3 nanosecond setup slack. Okay, so this is what we call the useful skew, right? This 3 nanosecond, we can use this. We can use this extra skew here to delay this clock and make this pass. So this is what the tool does. Okay, so by understanding what useful skew, how the tool does it, it can also help you manually doing this if you need to. Okay, we don't do this manually unless the tool cannot do it, or at the very end you only want to touch a specific type, only one path you want to do it manually. So understanding this is the first is violated by 1, the second path is 3 nanosecond. So let's go see how this works. So since flip-flop 2 to 3 has 3 nanosecond useful skew, we can use this to useful skew for flop 1 to 2 by adding 2 nanosecond delay to clock path to 2 and remove the setup time violation. Okay, so how do we do that? As you recall, okay, this was 4 nanosecond, right? So what we can do, we can delay this clock by 2 nanosecond, okay, then that will make this pass and also this pass. So let's take a look at that. So we're gonna delay this clock, capture clock of the first path 2 nanosecond. This is the launch clock of the second path. Okay, since this path original has 3 nanosecond skew or slack, so we're gonna add 2. So what happened here? Let's do it again. So clock delay is 2 plus 9 plus 1, so the data arrival time is still 12. Okay, but the required time is 10 plus clock delay. Now is 4 instead of 2 minus 1. So now the required time is 13 nanosecond. Okay, so now we have 13 minus 12. Now we have a plus 1. So it met timing here. Okay, so does this cause issue here? So take a look. So in the same calculation manner, so clock delay now instead of 2 is 4. Plus 5 plus 1 is 10. Recall it was 8 nanoseconds arrival last time, but since this delay by 2, now it's 10. So required time, clock period, 10 plus 2 minus 1. So now required time is 11 nanosecond. Okay, so we take the required time minus arrival time, we still have 1 nanosecond slack. So basically we take 2 nanosecond of useful skew here, we push it to the front. You remember we have positive skew and negative skew? Remember what positive skew helped? Positive skew helps setup time. So here it was 0 skew, so we added 4 nanoseconds to the capture. So you remember the skew by capture minus launch, 4 minus 2 is 2. So we added 2 nanoseconds of clock skew. Remember, positive clock skew helps setup time. This is exactly what it did, right? It was violated by 1. We added 2 nanosecond clock skew here and become a plus 1, right? And here we actually subtracted, we delayed this, so this become negative. So it was 0, now it's a minus 2 nanosecond. So negative skew is bad for setup. So it took away 2 nanosecond of setup time from here. The negative skew is bad for setup, but good for hold. Okay, that makes sense. It's a lot of data to digest. Okay, so because we have slack on the next path, useful skew, we're gonna use it to help this guy. I mean, the same thing. It could happen vice versa, and we just depend on what's happening. We can use a skew the next one to help. So the tool does it a lot, quite a bit. So in any other tool, you turn on the useful skew. This is a switch. I think by default it's on, and the tool actually uses to basically use the slack on the next path to help the other path, the neighbor path to pass. Okay, so yeah, let me go back. So a
So Bob,
question.
a question come in.
Okay.
Actually, a couple of questions. Might the useful skew technique mess up the global skew?
No, usually the useful skews are going to be local. It's within the block skew group. It's neighboring. So it's I mean rarely it's going to mess up the technique because it's looking overall, right? The global skew will look at overall the shortest and the longest path, right? So these are neighboring paths that kind of you divide it up. I mean, it's rarely is going to mess up your global skew unless this is like the shortest path, and then you change this, then that kind of impact. But it very seldomly does. Okay.
Okay. The
Um.
follow a different question from another student is, do we need to check hold in that same path to check hold slack, have enough margin so that we won't violate hold slack?
Yes, so this is showing you the setup aspect of it, but yes, in the same manner, it's you have to be mindful of if this fire hole, then the tool won't do it. Okay. So yeah, there's another aspect of this is a whole time check, correct. So I'm showing you the setup, the hole work the same way, but it's opposite, right? Because if you add slack, it's going to bat for hole. So in this case here, this is bad. It's good for setup, bad for hole in this guy. Here we make it negative, so it's bad for setup. You see the setup go from +3 to a +1, right? So this is good for uh the negative is good for hole, help the hole. So here I'm not showing you example of hole, it just complicate more things, but it's the same in the same concept how it's being used. Okay, so in reality is in the tool, it will do this. It also check for hole at the same time to make sure that doesn't violate hole. So if this violate hole here, it will not do it. Or if you set a priority, then you know, it usually hole has priority over set up in term of violation because hole is you cannot have hole violations, right? Setup you can, so hole usually take priority over setup in term of whenever we're trying to fix things. Okay. But you can override that fact. Okay. So this useful school concept is very important. You need to be able to understand this. So this will help you quite a bit in terms of trying to fix, trying to manually fix things at the very end of the design. A good engineer, the difference between good engineer and not so good engineer is that you understand these concepts and that you can limit the scope of the tool because at the very end you don't want the tool to touch it because the tool will mess up other paths. Imagine if you every timing's all good except one path here, and you say okay, let the tool fix it. You know what? It goes and it touches other paths surrounding it mess things up, and you end up mess up your design. So a good engineer understand this technique. You say okay, well I understand this is the path. I'm gonna go and manually fix it myself, okay, and not let the tool touch it. Then you will arrive at a solution much faster than if you let the tool touch it in most cases, if you have like one or two paths left. If you have many paths like hundreds and you let the tool chew on it until it come down to one or two, then you manually fix it. Okay. So this applies to both setup and hole. Okay. So depending on if a hole, depending on which direction where the violation is, whether you need to speed up or slow down the clock, right? So slow down clock will help hold, speed up will help set up. I mean, I'm sorry, slow down clock will help set up, speed up, the clock will help hold. Okay, makes sense? Any any confusion? If it is, I'll try to explain again. Okay, so you can see no skew, right? It's zero skew across, and there's 3 nanosecond setup met, which we call useful skew. Okay, we can apply it. So the reason it's 3 is 1, so we can apply 2 to make this pass or both pass. I mean, you can just apply 1 and make this at 0 and this at 2. It's still going to pass, but you don't have much margin. So here, example, I just add 2. Okay, so you add introduce skew to here, so you slow down the clock, which help the setup time, but back the whole. Okay, and here you add basically on this path, you add 2 nanoseconds, so you introduce negative skew. So 2 minus 4 is a -2 uh, clock skew, right? So minus skew is good for whole but bad for setup. You can see clearly. So now I hope you understand what positive skew and negative skew, what's the impact, okay, how it impact timing. So I just show you based on this useful skew, how it impact your timing. Okay. Any more questions? Any other comments from the my colleagues instructor? Okay.
Yes, but so for me, usually the way I look at this is sometimes the way I look at it is whenever you have like back-to-back timing pad, and then when you have one is negative and the other one is positive, then the way to look at it is you can adjust the arrival of the middle flop, right? Either to make it faster or to make it slower, right? To adjust for those, to make use of those positive slack, depending on the first stage or the second stage. So I think that's make it kind of like easy to kind of like remember, right? So essentially, you have two periods, and essentially you want to play with that, as long as the sum of those two stages is less than two, then you good, right? So and in reality, usually this is very useful when you have the first pad. Let's say flop one to flop two. The read, let's say you read out from the memory. Usually the read out time is like almost a period already. So you never gonna meet timing, right? So you have to borrow. Essentially, you have to use you have to delay the clock really, really extremely, it's kind of like eat up like another half cycle to give it enough time to meet setup for the read out, from the memory, and then you try to squeeze, the second stage, right? So
Okay. Thank you, Thane. So students, okay, so this technique is used. Okay, first of all, I guess you may say, why do we use this? Okay, why don't we fix it? Why don't we speed up the data path? That is the first option. Yeah, so the first thing you want to do is you want to speed up the data path like we normal fixed timing, right? Let's speed up the data path. Okay, fixed timing, and slow down the data path for fixing hole. I mean, that is the first options. Okay, so when the tool can't, once everything's in, when the clocks are in, before clock, you can't use this technique, right? I mean, you use technique with the zero clock is it doesn't, okay? So only the clock tree is in when this makes sense. Okay, real skew coming in. But the first option is to fix, speed up the data path, buffer it up and use those technique, right? Cloning, restructuring, things like that on data path to meet setup time. But at the end, you cannot. And once everything's in, it can't be done. Then this is what the tool does. Useful skew. Okay. So it's not that the tool will do this first and then speed up the path later. No, it speed up all the paths first, and and then the clock's in. It can't do anything else. Then when everything's settled, and then it'll take a look, analyze across the design, see where are the positive slacks, and it can be used for the neighboring flops. Okay. Any questions? This is important concept in terms of useful skew. Okay. No further questions. Move on to the next topic. Okay, so we just finished useful skews, virtual clock, generated clocks, and then some of the CTS optimist technique with load level adjustments and so on. Okay, so next thing happening here is actually the CTS process. So okay, so what happened during CTS, the tool does is the first thing it does is called clustering. Okay, and basically that just cluster all the endpoints together. Okay, all the sync together based on the skew group. And then the next thing it does is balancing. So what's when it does skew balancing per group. Okay, and then it does after that, it route the clock tree. So your clock tree will get all your clock nets will get routed here. And then the last step is called post conditioning, which is fixing minor timings violation that's left over. So that is 4 different stage that's happening during CTS. Okay, so what is clustering? This is the first step where the tool actually group the related sinks, you know what sinks are, just flip-flop into a cluster. So it does based on the skew group. Remember what skew groups are? It's basically a bunch of endpoints get grouped together that share the same clock source. So here example, this is one skew group, right? Clock 1. So you take all endpoint and cluster it, okay, and put it together and place it nearby. Okay, so this is just represent different, just a simplistic way of representing different clustering. Okay, so but during this step, it does this, it only consider DRV. It doesn't look at anything else. Okay, it build this clock tree and cluster based on the DRVs. You remember what these DRVs are? Max final, max trans, max cap. Okay, those are the DRV rules that the clock trees has to obey those DRV rules, just like the signal nets, right? In placement, we talk about DRV, that's applied to signal nets. In CTS has to obey the DRV rules also, and it's on the clock nets. Okay, but the DRVs on the signal net still being fixed in CTS also. Okay. Okay, so CTS build clock tree and place clock drive at a certain location distance based on the CTS DRV constraints. Okay, so max cap, max fan, max loads. So at the end of clustering, the tool report the number of buffers, inverters, ICF added. Okay, so there is 3 type of clustering. Just FYI, knowing this, I don't know if it's gonna do any difference, but it's called top-down clustering. So the tool start from a single cluster containing the sink and recursively split into a smaller cluster. Top down, the other one's bottom up. It begin from the individual sink, come back up. And then the other one's called iterative clustering. Combine top down and bottom up. So it approach both bottom up. I know this, I'm not I know that actually I haven't used it for anything, but just know what's happening, that's all. Okay, so just there's clustering, there's 3 types, that's it. But I'm not sure knowing this will actually help anything. I haven't used it to debug or done anything other than it's clustering method used. Okay, so that's first step, clustering. So this is the clustering log from Innovus run. So you can see stage called clustering during CTS. If you look at the clustering, so it's before it's the initialized clustering. You see the clock back. You can see the cell count. This is before. So buffers 0, inverter 0. There's 34 ICG on the clock path right now. Okay, and so on. It's total 36 cell. Okay, so this logic gate, I think this is a mux. Usually this the only things in here is going to be a mux. Okay, it's gonna be before CS happen, gonna be ICG cells or mux. So this is 2 mux. Okay, yeah, here it is. It's 2 mux, right? So 34 is 2 mux. There's nothing on the clock tree come from synthesis. Okay, so this is others. There are total 11,537 sync point flip flops. Okay, so this is your number of flip flops. Okay, other stuff doesn't matter at this point. Okay, so this is the clustering. So after it's done clustering, you can see here the cell count buffer, it added 209. Okay, and of course ICG cell should be the same, the mux is the same. It doesn't do additional unless you force it to. But so now after clustering, so it added 209 buffers. So remember, this is by default added buffers. You can change it if you like. Okay, I think in the tickler script I had a comment in there somewhere that you can change this the attribute, the keyword. Okay, so it added 209. So you buffers. Okay, so it tells you, and let's see what else it tells you. Okay, well the error went up obviously. So same. So that's it. That's what changed. It added number of buffers in there. Okay, and the let's see the wiring caps, things. Okay, cap down. Okay. All right, so during clustering, you can see what's happening. It add buffers build tree based on DOV only. Okay. So when you run in the lab 8, when you run CTS, you look at log file, you see search for the word I highlight, the keyword clustering, and you see what happening. Okay, so if you change all buffers, you can, all inverted, you should see this number. Maybe just slightly less because this design very small. Okay, it's very small, so it may be a not significant number. It may, maybe just slightly smaller because the design is very small. Only 11,000 flops. The real design, you're gonna have, millions of flops. So, okay, so the next stage is balancing. So during this step, the tool actually balances skew. Okay, so after it create cluster, build a tree in clustering based on the DOV, here is actually going to balance the skew. Okay, so again, it's going to look at the clock group and the skew group, and it's going to do per skew group here, right? Remember, if you don't define a skew group, it's going to cluster into one. Okay, in our labs, I believe we have maybe 6 skew groups, I recall. Okay, so the tool repeat this until all the skew group are met or already exhausted all options, meaning it try everything. If you have a challenge design, it try everything, it basically give up. That's all it can do. And you still have, you still have a large skew. Then you need to take a look at your full plannings and so on. Okay. So that's balancing. So you'll balance all different branches in the skew group. Okay, makes sense. So the tool first does clustering, build a tree based on DRV, and now it go back for skew group and it'll try balance the branches. So it's going to add buffers, addition buffers, or take away. Any questions? So these steps happen automatically when you tell the tool, okay, CC op design, which is a command that Innovus use, and then it'll actually go do all the steps, okay, internally. So it's good to know what's happening during the step, and as you look at log files, it'll help you to debug the issue. You kind of look at the log file. Okay, so this is balancing the stage balancing log file from Innovus. This is from our lab. You can see just search for stage balancing, and you start seeing the log file. So here, two skew group, right? It tell you all different things here. I don't really exactly know what these are. Solving LP. Okay, so basically I look at all this. Okay, so try balancing. Try 252 succeed. Okay, 0, 6, blah, blah. Okay, so total reducing skew, 0 average skew, 0 net. So this, okay, so it's happening here. So, okay, it's reducing net. And then it's after. Okay, what is it? Does it do? Okay, so it doesn't really improve, do much in this stage. I think we had 211 last time. We had 209, so it added 2. So look like it built a skew in DRV. So the clock tree here is not very challenging. After the stage, it only added 2 to balance the rest of the tree. So this design is small, so it's not very challenging. So it only added 2 flops, 2 buffers to balance the skew balancing. Either that or our target is not tight enough for it, challenge enough for the tool, for the type of design, for the floor plan that we have. Okay, so it add only 2 to improve the clock skew. Okay, so the next stage is once it goes through it goes
But
through clustering.
can you go back to the previous slide? I think that's the skew number, right? Can you compare the before and after? The skew root?
Yeah, so the skew over here. The insertion
Yeah.
lay is okay, let's go back. Yeah, the point. Yeah, the insertion lay min and max is so the difference between the min and max gonna be your skew, right? So one, two, actually a two skew group. You want to compare this number to so here it doesn't have the skew, right? It doesn't report the skew here. So here it's only based on DRV fixing. There's no skew numbers reported here. Only after the balancing it report the skew.
All right. So you have 0.316 versus 0.8, right?
So that's probably before see 0.8. Yeah, it doesn't report here. Oh,
so
it's
whenever
probably
you just
somewhere in the log file. This is a snippet from just the before and after. Yeah, probably somewhere in the log file. It probably show it during the clustering somewhere along the log. But this is just the before and after. I cut stuff out between.
right. Okay.
Yeah. So it probably show it in there. Yeah. So we have this is the scan clock, and this is the functional clock. Okay, so both in the 300. Okay, anything pointed out. Okay, so routing clock trees. So after it does clustering and it balances the clock tree and the skews are and insertion layer are met. So it's going to route the clock tree next. Okay, so the clock tree will obey the NDR rules. Remember what NDR rule was? We had an example of double space, double width, right? And sometime you can add shielding, but I believe in our lab we just have a double width and double space, so that will get applied. So in the lab when you route it, you can take a look at to make sure that those rule 2WWS get applied. You can do that by just click on the clock net and hit Q, and it'll show you what routing rules and so on status. Okay. So all the clock nets are normally get routed in higher layer metals. Remember, believe in our lab, we wanted 3 and 6. Okay. Um, okay, so I'm gonna stop here and ask you guys, why do we want to route the clock nets before now versus wait until routing stage and route with the detail, route with the rest of the signal nets? Why do we want to route it now? Why not just wait until the next stage and route at the same times? Okay, feel free to chime in on the chat. Okay. I think is this one of questions in the pre-assessment quiz? I did the pre-assessment a while back, so I think it was on there in similar questionnaire. Okay, the reason anybody want to take a stab at it? Okay. Reason we want to route the clock nets first is because okay, oh there we go. Okay, let me oh okay, I see it come up. Let me go look up here. Oh, dope. Okay. I'm having issue with the chat. Okay, Novokai said because the clock is sensitive signal and have double space, so we want to reserve the routing resource for it to ensure the clock is best recommended. That is right, because that's correct. We want to, yes, we want to ensure the best path available for the clock next to route, the shortest possible, right? And so that's the reason. Okay, so like I say, because clock is sensitive signal and have a double width, double space, so we want to reserve routing resource for it to ensure the clock tree is best routing condition. That's right. We want it to route the best chance as it can without detour. So we want to have, all the tracks available for it to route first. That's correct. If we route Figma first, we don't have enough space for clock nest. That's right. And we want to make sure, yep. We want to make sure the best path to have the best skew. That is correct. Yep. Good. That's all correct answer. Yeah. So the clock nest is so important to the design, right? And the clock nest can impact your design in closing timing for your design and operate reliable on your design. So we want to give it the best chance. So design's wide open right now. Route it first, the best possible path, the best possible clock you can get. And then we throw in the signal later. But if the signal come in, the clock might have the detours and so on. So the clock path, you have more skew basically, and the clock is not may not be as good as it can if you route it first. Okay, good. All right, next question I have is why do we want to route on the higher layers? Why not route on metal 1, metal 2? Why do we want it higher layer 3, 4, the middle layers? Yeah, I'll give you minutes to think. Okay, anybody? I think in the last, if you remember the last lecture, Mr. Okay, so can you say lower R in higher metal layers? That is correct. So the higher metal layers usually have less resistance. Remember, resistance reduce speed, reduce delay. It's the biggest impact on delay. Okay, so we want the signal to get there faster, right? And reduces the insertion, reduce the clock skew. So the higher layer is going to help us do that, propagation delay on the clock. Okay, so if there's less resistance, the faster signal propagation, you're going to reduce overall clock skew. Okay, and a high metal also have less resistance, so less IR drop. Yes, that is correct. Reduce crosstalk. Yes, it's reduced crosstalk in terms of power distribution. So if you do a lower layers where like 1 and 2, because metal 1 uses a lot of power distribution to the standard cells, that can be a lot of noise down there. So yes, that's also true. So low latency and power. Power actually power is going to be opposite. Is you're going to increase some power because on a remember higher layer, right? It's going to be wider metal, less resistance. The low capacitance is going to be more on the higher layers. So we actually sacrifice a little bit of power or wider metal to have a better clock tree. Okay, overall clock skew. So it's actually opposite. So wider metal is actually the loading capacity is going to be much higher on the drivers, but that's a small price to pay versus having a better clock trees and better performance for your design. So you sacrifice a little bit of power. Okay, good. So great. All right. So any other questions on clock? Why we route clock trees and why we do it here? And Any input thing you want to have anything to add?
No, I think you guys
Okay.
covered very well.
So Nguyễn Nam Hải say why high metal layers are less congested than lower layers. What I mean less congestion, meaning in terms of power distribution. So if you remember the lower layers here, you see the lower layers, metal one, you have a lot of power coming. This is all power feeding ground provided to standard cells, right? So if you build on the lower layers here, it's be more crosstalk. Okay, not in term of congestions per se, because it's wide open, right? It's wide open, but it's more induced crosstalk. You want to avoid this because there's a lot of power and ground here on the lower layers. So you sit right next to it on top metal two. Okay, so you want to avoid one and two usually. Okay. So lower layer mean like metal one. Okay. Metal one and two for that reason, because of the power distribution noise. Also, there's a lot gonna be more vias too. You know, there's a lot of via coming in on metal one, Okay. So remember what via is. Via is just a connection between a jump layer. When you go one and two, there's a via connection between. Okay. So we want to avoid lower layers because of that reason, the power distribution noise. And also that higher layer have less resistance. You have better clock tree. Okay. All right, then we'll go to okay, so this is routing clock tree logs. So you can see clock detail routing. So that's the keyword. So once you do your lab, open it up. Once you run it, the log file, search for clock detail routing. You see what's happening in this stage. This is just the first and the last. There's a lot of thing between that you can see what's happening. So this is just the, you can see what's happening at the beginning, right? Total of non-default rules. So this is telling you, okay, it sees a non-default rule. This is NDR or having extra spacing 250. Okay, so there's 250 nets having extra space that it apply the rule to. So it's 250 clock nets. Okay. This is small because it's a small design, but it'll tell you what it sees here. Okay. So after the routing, the DAG, still the same number of buffers we see. We should expect the, let's see, transition. Yeah. So what happened usually? Does anybody know what happened to the timing numbers when the clock trees get inserted? So when your clock tree is routed, does your timing number get better or get worse? Meaning your setup timing, your hold timing, and then yeah. So the usually get worse or get better? Let's pick setup time. Does it actually your setup timing? Does it improve with clocks in, or does it actually get worse? Or there's new violation come up. Let's say you were close your timing before the clock's routed, and now clock's routed in. Does your will can there be new violations due to clocks being routed? The answer is yes. There you may have closed your timing without a clock she's routed in. So those okay. There could be new DRV, there could be new timing violations. Okay. That's why you need the next steps, what's called post conditioning. Okay. So when there are new things pop up, this step will actually gonna fix some of that. Okay. So basically just so the clock tree is routed, that mean the clock tree up the clock are propagated, meaning that all the delay will get propagated, the real delays in per segment per clock. Okay, so this step fine-tune the skew. So it'll with the clock tree routed, it'll take a look at analyze everything's again. And if there are issue is there's if there are opportunities for us to improve, it's going to do that. Okay, and also it fix any minor timing or deviolation after clock is in. Okay, so I said these new violations arise as a result of newly routed clocks, which cause degradation in timing on DRV. Okay. So I show here, I think I show here just the concept of before and after. So this is before CTS. We have no latency, no clock delay, right? And this is just the top headers of your timing, your detailed timing path. Okay, so if you look at like for example, rest to rest dot ta.time rpt report, you'll see this at each of the path. So my main point here is no latency. Okay, no CPR adjustment. Here, after clock tree, you can see the latency and you can see the CCPR adjustment, right? This is the common path minute removal. You can see the adjust. Okay. So that's the main point that I want to point out with this two before and after headers.
Yeah, I think is that I is for ideal and P is for propagated, right? So
Yes. So this is ideal clock. Like Mr. Ting said, the P is for propagated. And then the clocks are in. Yeah. Yeah. If you in the lab, I mean I don't suggest just I want you to actually go in the log file and see what happening, understand, and look at the time report. For example, after CTS for initial, if you have time violation, take a look at the summary file, and then if it's a rest red, go open the log file on the report directory and look at it at that particular, and then see the violation, and then pull up the timing, the timing debug graphs and see where the violation, which cells and so on, and highlight the path, which in the previous lab you should be able to do that and kind of see what's going on. And then in the lab, in the next lab, also you bring up the clock tree debugger. You can see, where are the worst path, what contribute. So instead of just running through the motion, run the lab and say, oh, I've done it. But make sure you understand, go into the lab, go into the log file, go into report files, after placement, after CS time evaluation, look at it and see what's happening before you actually run optimization. Okay, and understand what's happening. That way you can help guide the tool or actually manually fix things if you have to. The more you understand, the easier it is for you to try to control the tool, set some constraints and guide the tool. Okay, so there's a term called garbage in, garbage out. So garbage is trash like that, right? Garbage in, garbage out in PD. So you put in garbage in, it's going to spit garbage out. Okay, so I mean that term used a lot here. So garbage in, garbage out. You throw in garbage in it, meaning poor constraint, you're going to get bad design, bad result coming out. So you have to understand your design and how to fine tune things if things go wrong and fix things. Okay, that's what a good PD engineer does, understanding the detail instead of go motion. Okay, so just imagine if you go to work and then you got a design and then it's a timing challenge. Okay, trying to push performance, and you keep push all the buttons on the tool, but then it's still bad. You still not achieve. Okay, so you have to be able to analyze and see why. What's the issue? Is it architecture issue? Is it floor planning issue? Okay, and after you exhaustively trying to fix it manually and things like, okay, you can't do it, and then you say, okay, you have to have all of your reason before you go back to your boss and say, okay, this is impossible to meet timing due to this after I've done this and this. Poor architecture, poor floor planning, or whatever. Okay. So if you just throw your hand up and say, I don't know, boss, these can't run. You don't have data, and you didn't show you tried all the method that's available to you. Okay. Then it's bad, right? You want to understand these concepts. And anyway, you'll get to do this on the final project. So the final projects will be available soon. Next month, I think. Okay, so post conditioning. This is a post conditioning log. Okay, so you search this, you can see what's happening here. It's still trying to fix the DRV upside. on the clock trees and so on. So yeah, so you can search the log file and see more details on what's happening during post-conditioning log. I think that's it for this lecture. So we got two minutes left. I'll leave it open for Q&A, questions and answer. Okay, so next week is going to be pretty much we come to the end of CTS. So next week gonna be just a couple, very few slides in terms of lecture because we're pretty much coming into CTS. Next week we just have, believe, just validate how we qualify the CTS output and so on, and then the labs, lab number 8. Well, not next week. This coming week is this coming Friday. So okay, no questions. So hopefully you guys pick up this concept, CTS. Okay, a different technique, how the clock being balanced and different thing, and useful skew. How's that can be used to fix timing and set up and hold. So yeah, take a look at it. Take a look at the slide again and understand that, and then we'll go through the labs, and perhaps you can, if there's an issue like that, there's opportunity you can actually apply it. Okay. All right. Anything else?